Hey everybody, welcome.
Hey.
Hey, a little bit of audience participation helps a little bit here, so feel free to talk back to me. So I guess you're either here for extra credit or you're here because you're actually interested in the movie Interstellar. Some of you I see here are not in any of my classes at the moment, so I think you're actually here for the interest of it. So that's pretty cool. But that's basically what we're going to go over. We're going to go over some of the physics here pretty lightly to hopefully give a better understanding of what was going on in that movie. I'm not going to get too deep into it. The last time I tried to talk about this kind of stuff was a few years ago, and my wife kept telling me it was too much math. And so I took the math out, and then she said it's still too much math. So I took more math out, and she said it's still too much math. So I don't think I really have very much of what you can call math in here, which is very disappointing to me, but we'll deal. So I'll try my best not to over-explain things and get down too much in the nitty-gritty, but we'll see what I do. So you've probably seen some movies that have some time travel in them, right? So the one we're talking about today, Interstellar, we can see over here a couple of my favorite ones, Back to the Future, greatest movie trilogy of all time. Yeah. This was the time sheet. Oh, Bill and Ted, Terminator, Edge of Tomorrow, and Groundhog Day. Those were great ones. Does anybody know this one? Other than Madeline?
Is that 12 Monkeys?
That is 12 Monkeys. Yeah, that's 12 Monkeys. Which, by the way, if you've never seen, great time travel movie. Very, very interesting. Very, very different kind of a thing than what we're talking about here today. But most of the other ones, they always have some sort of paradox in them where they went back and did this, but if they went back and did that, then they would have had no reason to go back and do that, so they wouldn't have gone back and done it, kind of a thing. 12 Monkeys is not like that. That one's really good. So anyway, we're going to get into Interstellar because Interstellar actually had, or at least they actually put a lot of effort into being at least as scientifically accurate as they could be. They brought in Kip Thorne, who is like the world expert on black holes right now, and he did a lot of the science for them as they were making the movie. So they'd say, hey, we know this, is this possible? And he'd be like, well, let me go tell you. And he'd go off and come back and say, actually, yes, that is possible. So you can do that. They even named one of the robots in it after him, Kip. If you ever watch it and notice one of those little robots they have is named Kip. So what is a black hole to start with? This is not a real photo of a black hole. We have like one team that thinks they got a real photo of a black hole, and it's kind of debated, but we'll see. And then this is more like from a simulation of it, and it's kind of crazy looking like that. But basically, this is a region of space where you have so much matter all compressed down into such a dense point that not even light can escape from it. Like if you try to throw a baseball up into the air, it's going to come back down, right? There is a speed at which you could, and for my physics classes we will get to that you could, if you were really, really super, super strong, throw or launch a baseball at and actually have it not come back down, all right? Well, black holes are kind of like that, except that not even light, which is the fastest thing in the universe, is fast enough to escape from it. So once you get within a certain distance of it, that's it. There's no escape anymore, not even if you're as fast as light. All right, and in fact, that place that we call that is the event horizon. Okay? Event horizon. If you get past that point, the idea is that's it. You can't get back out, you can't get any other information back out or anything. So, what did I just do? I went the wrong way. There we go. So before we get into this, we need to talk a little bit about relativity, and this is Einstein's theory of relativity. I'm not going to do a lot of differentiating between the two main types of relativity. There was one from 1905 with special relativity, and then there was the 1915 one that added in gravity. So we're going to just talk about relativity in general. But basically, the idea is that, or two big ideas in it, is that everybody can consider themselves stationary. All right? I think he had the old question of, does the chicken cross the road or does the road cross under the chicken? And so the idea behind this is that everybody or everything considers themselves as being stationary, and that the rest of the universe moves around them, and that all the laws of physics are going to be the same for everybody, no matter what. There's some weird things that happen out of this. If you want to go watch my videos on relativity, where I did like 4 videos of that, that explains kind of the weird stuff where it seems like stuff doesn't match up and everything, what we do about that. Those are on the Torch Talk video, so you can go do that. And the other thing we have that we're mostly interested in here today is time dilation. And basically the idea is that if you're going really, really fast, and I'm not talking like you got in a NASCAR car or in a jet airplane, I'm talking really, really fast, near the speed of light. The speed of light is about 186,282 miles every second, which is about going around our planet about 7 times every second. So if you start getting near that kind of speed, which no human really has ever come anywhere near that, not even close, time will start to slow down for you, noticeably, right? It'll change. And also, if you get into really strong gravitational fields, time will slow down. And so we're going to get into why that started. So originally, people found out that light was a wave. And one of the things they knew about light or waves was that all waves had to have a medium, something through which they went and traveled through. For example, I'm speaking to you now, and you can hear me because I am creating sound waves that are traveling through the air, which is the medium through which they're traveling, and then over to you so you can hear it. So some experiments started showing that light was a wave. And the idea was then there must be a medium, because light was traveling through space. There must be a medium that permeates everywhere, all through all space, and then light travels through. They called this the luminiferous ether. And Michelson-Morley, they got and developed an experiment to try and figure out what the actual motion of this luminiferous ether was. We're going to call it ether from now on. As we move through it. Kind of like if you were on a boat or something moving through the water, you would be able to look and see that like if you were swimming through the water, you see waves coming off the front of you that are kind of shorter, and then the waves coming off the back of the person swimming are longer. And if it's a running water or whatever you want, it's going to change how the waves move around you. And so they came up with this idea to do this where as Earth went around the sun and we orbited and everything like that, that different directions would be traveling differently through the ether. And so we should be able to detect that difference. And they came up with what is called their interferometer. They basically just shot some laser light, split it, had one go straight, had one go off at a 90-degree angle, and then had them come back and see how much the waves got out of sync with each other. And by finding how much those waves got out of sync with each other, they could basically tell how we were moving through this ether. And tell, basically, in other words, it's kind of like if you could throw a baseball 50 miles an hour and you're in a car going 50, and if you throw the baseball out in front of you, the 50 plus the 50, the baseball would go 100. But if you threw it out back behind you, it'd be 50 minus 50, it would just drop to the ground. So they wanted to detect this relative velocity of light, and it turned out it didn't work. And no matter what they tried, they couldn't get it to detect a difference in the speed of light, no matter what direction they pointed this thing. And so this was a big deal, and a lot of people were like, what do we do about this? You know, there's got to be some reason for this. And it was Einstein that eventually came along, and he basically said, you know what, we're going to accept that this is just something that is true in nature. The speed of light is always the same, no matter how you're moving, in what direction you pointed, or whatever you're doing. When you measure the speed of light, it's always going to be the same number. And he said, what's the consequences of that being true? And pretty much all of relativity comes from that idea. You know, let that be true, and what follows, follows. So that's one of our biggest things. Speed of light in a vacuum, always the same. So if you get in a car and you're driving 50 miles an hour and you shine a laser light out in front of you, the laser light going out in front of you doesn't go the speed of light plus 50 miles per hour. It goes the speed of light. In fact, if you're in the car and you shoot that laser beam out and you measure the speed relative to you as you're driving along, you will measure the speed of light. Someone standing on the side of the road will also still measure the exact same speed for it. That's not what would happen with the baseball. If I measure the speed of the baseball after I throw it from the car, I'm going to measure 50. The person on the side of the road is going to measure 100. okay? But that doesn't happen with light. And there's a lot of very interesting consequences of this. So first thing I want to introduce you to is a time clock, or a light clock. And really the only way, and it kind of takes a lot of thinking, and I'd love to get into this, we can talk about this for a long time. The only way to measure time is through this consistent speed of light, okay? And we have a light clock for this. And the basic idea is you just have two mirrors that are a certain distance apart. You send a little particle or a little wave of light up, and then see how long it takes for it to come back. And that's 1 unit of time, whatever it is. Say you set it up so that it takes half a second to go up and half a second to come back down. Every time the light bounces there and back, it's been a second. You can keep track of time every time you see it come back down. All right? So that would be the example in the top. But now imagine you have your light clock, right? You have your light clock, and you start moving this way with it. All right? Now I have every right, as I'm moving along sideways here, to claim that I'm not moving, like if I'm on a train or something like that. To me, I still have that top situation. I see the light go up, and I see it come back down, and I say, all right, it's been 1 second. The speed of light, the distance between these two things gives me it's been 1 second. But if you're standing on the side watching me go by with my light clock doesn't appear to shoot the light straight up and straight back down, does it? It appears to shoot it, and then as the light goes up, I move to the side, it hits, and then comes back down. I reach the stairs, I gotta stop. Okay? So the path you see is more like this one. And what can you tell me about the path you see here compared to that path up there?
It's longer.
It's longer. This is a longer path. So quick question. If you're going a certain speed, and you have to go a short distance and a long distance, which one's going to take longer?
Wait, no.
Got that one backwards. The longer distance is going to take a longer time, right? Because at the same speed, it takes longer to go a further distance. So this is the exact same thing that's occurring. So we shoot out one little burst of light. On the train, I see it go, and like I said, it goes half a second up, half a second back down. I say 1 second has occurred. You standing on the side watching me go by, does 1 second occur? Because if you measured that speed of light, it'd still be exactly the same as it was. That's what experiments showed us. No, it'd have to be more than 1 second that went by. Maybe it was like 3/4 of a second and 3/4 of a second, and we ended up with 1.5 seconds rather than 1 second that went by. It really depends on how fast I would be moving next to you. Okay? And so you can see that just by moving quickly, we can actually have something, or at least between two things where one is moving and one is stationary and the other one is moving kind of thing, we can have this idea of measuring different times for the same event. Now, the person on the train, all the laws of physics have to be the same, so his watch should slow down, everything should be different to the guy standing on the side. All right? We can actually get a whole lot deeper into this because you might, bake your noodle by also pretending that the guy on the side has a light clock and the guy in the train is watching him. And then the guy on the train says, when his light clock, he would say the opposite, that the other guy's clock is going slower than his. So there's a whole lot there. Maybe if we get at the end, we have a few extra minutes, I might tell you the solution to that one. But that one's crazy interesting too. Oh, I see I got your interest there, huh? It was called the twin paradox. The idea was you took two twins and you put one in a spaceship and you sped him off really fast near the speed of light. And his twin stayed on Earth, and on Earth he sees that guy fly off really, really fast and sees his time slow down. And so he says, my twin is aging more slow than me, now I'm the older twin. But the guy on the spaceship looks back at Earth and sees him going slower and says, no. My twin on Earth is now the younger twin and I'm the older one. And so there is a resolution to that. It's in my videos, by the way, if I don't get to it today. So anyway, you all at least with me on time slows down when you move fast. Something weird happens with time. But also turns out that gravity itself can change time. All right, it can change time, and we're going to talk about this, a little further in this. But basically, it can shift light rays. And so, as you try to shoot light away from a very massive object like our planet, it'll actually stretch out. Okay? And so, say for example, you were in Florida and you're like, I'm going to send a signal up to the satellite there. You'd say, every second I'm going to make a new wave crest. Okay? But as it travels up, and you tell them this ahead of time, this is my clock. Every time my clock ticks, I'm sending out a new little crest in this light wave. Well, when it reaches them, it is stretched out, which means it's taking longer between the light rate, like the little peaks, to get there. So when they're reading your 1 second clock intervals, they're going to see it as going slower. Right? And the reverse happens. If you send something back into them, they're going to see it the other way because it's going to get compressed, and they're going to think your seconds are too fast. So, let's talk about Einstein's equivalence principle. Basically, what Einstein said, and this was, I think, about the most genius thing like I've really ever heard, is that you cannot tell the difference between acceleration and gravity. No matter what you do, without some sort of like visual, well, I think it looks like gravity or I think it looks like an acceleration, you can't tell. So, for example, let's say you were in a big giant train car and it was all sealed off and it was on a perfectly smooth track and you were just sitting there. You woke up on this train car, somehow you got in there, right? You can't see outside, you can't hear anything, it's perfectly smooth, straight track. Do you have any way of telling if you're even moving or not? No. Right? You know. Well, what if you were standing on this train car and you're like, man, I don't even know if I'm moving, and then suddenly you started to like kind of fall to the right? Well, that kind of happens when if you're in a car and a car turns left, where do you go? Right. Okay? So let me ask you a question. You're in this train car and you start to fall to the right. You think, oh, we're moving and we must be turning left. And then, okay, I can tell I'm moving. Well, how do you know it isn't more just that someone lifted up the left side of the train car? And now you fall off to the right as well. Well, what about if it speeds up? If the train car speeds up, you'll go to the back. Right? Like in a car. Accelerated car, you get pushed back in your seat. Stuff flies off the dashboard, whatever. But what if they just lifted up the front of the train car? Wouldn't everything slide back then too? And then what if the train was stopping? Then you'd fly forward. Right? Well, same thing if they just lifted up the back of the train car and it wasn't moving at all. So the idea is there is no experiment that you can do that would tell you whether or not you were actually moving or not. And whether or not the accelerations that you would feel in there would actually be accelerations due to gravity from tilting the train or from actually speeding up, slowing down, or turning. Those accelerations, indistinguishable from gravity itself. In fact, one of the neat things, and I think I even mentioned this in my physics class recently, is let's say you have a balloon with you, a helium balloon, and you're sitting there in the middle of that train, and what do helium balloons do? They go up, correct? So if they take and tilt the car over toward right, they lift up that left side, wouldn't the balloon go to the left? But when the train turns left, doesn't everything go to the right? Wouldn't that be a difference? But it's not. If you're in a car or in a train car and it turns left, everything goes right, the balloon will go left. It will go the opposite way. So let's imagine we had a giant box and we were out in outer space, there's no gravity, there's no nothing, it's just floating there. And we took a helium balloon and we put it right in the middle of that room, right in the middle of that box full of air. Okay, the helium balloon, and we let go of it. What's it going to do? Which way is up? It's not going to move, is it? It's going to stay right there in the middle, right? There's absolutely no difference anywhere. Now take that box and put it on a planet. You put the balloon in the middle of it, and it goes up, away from the planet. Well, why? Well, it does that because the air will actually get more dense down at the bottom of the box because of gravity, and there will be less dense air at the top, and it will go up to try and equalize that. When you're in outer space, the air is just equal density everywhere, and the balloon has no preferred direction. Well, what happens when you're on this train car and the train car turns left? Well, you go right, all the papers, everything goes right, so does most of the air. And you get a pressure differential where you get higher pressure on one side than the other, and the balloon goes the other way. Just like it would if someone lifted up that side of the car. All right, so it's really basically indistinguishable. And so that's what I have here. You've got a guy standing on Earth. This was my good picture. Pretty awesome, right? And he's got a ball dropping, and he's on Earth. Acceleration of gravity 9.8 meters per second squared. Okay? And he just drops the ball and he watches it go down. The other picture is a guy in the same room, totally closed off, can't see anything, can't even hear the rockets going, but there's a rocket booster going off, accelerating him forward at 9.8 meters per second squared. And he stands there and he drops the ball. Well, as soon as he lets go of it, it stops accelerating with the rocket that he's in, and it will go down to the floor at 9.8 meters per second squared. It would be identical between the two. So if you were in these two situations, you would not be able to tell whether or not you were on the planet or you were in outer space blasting off. The only thing that would tell you a difference is if you could look out a window and say, oh look, I see a planet that I'm standing on, or oh no, I don't, I just see stars and blackness. Okay? So do we feel pretty good about this idea that we cannot tell the difference between acceleration and gravity?
Yeah.
And so then Einstein said, if you cannot tell the difference between them, then you can't treat them like they're different. You treat them as though they're the same thing. In fact, he said, if you want to understand gravity, understand acceleration. Gravity, acceleration. So most of you probably think gravity is the thing that's pulling you down. Einstein said, no, 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 no. Gravity is the ground pushing up on you. So it's like we're being constantly accelerated upward at 9.8 meters per second squared. That's what sticks us to the ground. Okay? If this suddenly stopped accelerating, he'd float off the ground and start floating. But as long as it continues to accelerate, exactly the same as being on the planet. On Miller's planet, do y'all remember Miller's planet from this one?
Is that the
water
water?
Planet, right? The one with the giant waves. On that one, it was really, really, really close, deep in a gravity field near the black hole, and its time actually slowed down greatly because of this. In fact, if you want to determine how much time slows down for something, since our acceleration is the same as gravity, all you really have to do is figure out how much gravity would accelerate it between the 2 points, and whatever its change in speed is will tell you how much the time has to slow down. All right, that's why I spent so much time kind of talking about this. So if I drop something from like outer space over top of Earth, the amount of time dilation that's going to occur to it as it falls down is going to equal however fast it's going. It's based off of its speed when it gets down there. So you can actually calculate this based on just how fast something was going if it fell in. All right? And then, of course, I think as we remember, it didn't work out for them very well when they went down on the planet. And not just because that one guy didn't make it. All right? So it slows down very, very, very much near this black hole. And in fact, they said in the movie that 1 hour on the planet was 7 years to the people that stayed away from the planet, like up in space or compared to us back here on Earth that weren't in that strong gravitational field. And of course, what happened to them? They got stuck down there for a long time, right? By the time it came out, it had been like decades, right? So, it wasn't very good. Yep. I thought that was the best picture I could find of it. But yeah, Miller's planet, 1 hour for 7 years. Kind of crazy, right? So are y'all still with me here so far about this, or have I messed something up so far? Still buying what I'm saying? Okay? This idea is that if you were to fall down to that planet, essentially, if you were to start off in that state and you were to just fall down to the surface of the planet, you would be accelerated so close to the speed of light, you'd be going essentially so fast that it would cause that much of a change in time. Right now, if you got out and you got in an airplane and flew around the planet, you wouldn't notice the time dilation. The fastest planes and stuff go, or jets or anything like that, they are nowhere near the speed of light. I mean, you get in a plane that goes the speed of sound, The speed of sound is about 340 meters per second. That's like 3 football fields every second. How far did I say light goes in a year, or in a second?
7 times.
Around our planet 7 times. We are nowhere near taking people that speed, but we do actually see this effect. We can actually see it. We see it in GPS satellites. So GPS satellites, they're basically just a big giant time machine. Like, not a, see, I hesitated to say that. Not a time travel machine, but a big giant timekeeping machine. All right? What the GPS satellites do is they keep track of the time, and then down here we keep track of the time, and they basically broadcast their position and their current time. And then what your little GPS thing does is it takes in the current time that it's getting from them, looks at what the current time is and says, oh look, that one is, half a second behind what the time actually is. And so therefore I know at the speed of light, that satellite has to be a certain distance away from me. Oh, this one's 2/100ths of a second behind. I know that satellite has to be this distance away from me. And so you can basically figure out how far you are away from several satellites. And I see this a lot in movies. They call it triangulating your position. You ever seen them do that? They're like, oh, we can use the cell phone towers and triangulate their position. Yeah, that's not actually what triangulation is. Triangulation actually involves triangles. What we're doing involves circles and spheres. So what you need with GPS is 4 spheres that overlap, where you know the different distances to, and they'll end up being one point where all of them overlap for this. And then that'll be your location, because you know how far you are away from 4 different satellites. They do this with earthquakes as well. This is called trilateration. Trilateralation. I just don't pronounce things well, big words. Trilateralation, all right? Where you overlap circles and stuff like that. And then we can figure out where things are. But in order to do that, it has to be very accurate with time. Well, if we put this thing in orbit, where it's going really fast, and it's in a lower gravitational field, and all this kind of stuff, well, its clocks are not going to run like our clocks do, right? So the GPS satellites have to actually account for that and keep correcting their time to be like ours based on their motion and where they are. They have to actually account for it, or the system wouldn't work. In fact, I would go so far as to say that this idea of time dilation, time slowing down like this, we have tested this more than any other idea in science. It's not even close. We have tested this and it has passed every time. Way more. Think about your GPS. Every time your GPS accurately gets your position, which depending on how, whether or not you're running the GPS right at that moment or you're letting it go off, on your phone every 30 seconds or something. But if you're out and you're navigating, it's getting your position accurately every few seconds. And every time it does that, that's a little confirmation that the time dilation that they're putting in there, mathematically correcting this, is working when it gets your location correct. How many times a day do you think a GPS correctly gets somebody's location somewhere on this planet every day? That's a lot, right? That's a lot. That's a whole lot of trials for special relativity and this time dilation thing to stand up to and keep being consistent and keep working. So, and then one more thing on that, even with that much confirmation, and I guess the ones that know me know this, I will say, wouldn't call it a fact. Just thought I'd throw that out there. Can't prove it. All right, now this one I'm hoping is going to be okay. I kind of did these last minute. I had the idea of doing this. I talked about this before. I tried drawing them, and the drawings weren't very well. So I tried coding them. I tried making some codes to show these things. So what we have, and I'm going to show you first, and I really hope it's visible on the TV screens for you, because again, like I said, I did this last minute, are these things called space-time diagrams, Minkowski diagrams. And so what I'm going to do is flip over, hopefully. Nope, that didn't show up. Let me go back. Where was that? I'm going to have to come back to this. We're on 11. Can y'all see those lines?
Mm-hmm.
Okay. All right. So there's a few things on here And what you can see is this is what's called Minkowski space. And I wonder if I can just zoom in on this a little more. Can a little bit. We'll get over here in this upper right corner, and that's where we'll move over there. Yeah. All right. On the horizontal axis, we have position. So we're basically doing one-dimensional motion here. You can extend this out to 3 spatial dimensions, which really we can only draw 2 spatial dimensions on a 2-dimensional piece of paper. If we add in 3 spatial dimensions, this becomes a 4-dimensional picture. Okay? So we can't even draw a 3-dimensional picture, really, we can only kind of fake it. So we're staying 1-dimensional here for space. So on this horizontal axis, this is position. On the vertical axis is time, and we're multiplying it by the value of the speed of light, because that has a very interesting effect of, you see this dotted yellow line right here? That ends up being how a beam of light would travel through space-time. This is what we would call space-time. It's space and time that are linked together. And it would travel at 45-degree angles everywhere. So if we launched a beam of light from over here, it would travel at a 45-degree angle, just like that. This thing that you see here, the 2 beams of light like that, you can imagine if we had a 3rd dimension coming out this way, that would make a cone. And they actually refer to that as a light cone. Now, if light is the fastest thing in the universe, if you were just sitting still, right here, not moving, right? So you sent off this burst of light, those are the 2 bursts of light, and then you sat still, time would go on, but you would not move at all left or right. You just go straight up. If you try to move to the side, like you shoot off this beam of light, if you try to move to the side, like along this green line, okay, then you're moving in both position and time. All right? But you can never go as fast through space-time as light, which means if you're inside this light bulb, you're between these dotted lines, is there anything you could do to get out of it? No, because to get out of it, you'd have to go faster than light, which would mean you'd have to go past that 45-degree angle speed to get out of it. And it turns out we can't do it. We've never been able to do it. That's another one of those big consequences of this special relativity stuff. No matter how fast you're going, the speed of light always seems the speed of light faster than you. So how can you catch up to something that's always 186,272 miles per second faster than you? You can't. Okay? You can't. So what I also have down here is those green lines. Those are basically what you call, they're basically a set of prime coordinates. They're someone's moving perspective. From their moving perspective, their x and their time axes actually bend like that. Their x bends up like that, and the time bends over like that equally from both sides. All right? And if we took and we stretched them out, the other ones would bend the other way, and we'd say the green guy is not moving, and then the gray lines would become the tilted ones that we would think were moving. But what we can do is you can actually, I have this in here where we can adjust this. This is beta. It's the ratio of how fast the moving green person is going compared to the speed of light. So right there is pretty big. If you go down to, oh no. Uh-oh. So let's see here, let's try that again. Oh, now everything's turned on. Let's turn some of this off, make it less noisy. All right, there we go, we have that. And if I go down here and I slow this down, well, now we got some negative. If we go to 0, now they're both just sitting there, right? And as you speed up and go faster and faster, closer and closer to the speed of light, it gets faster and faster and faster and faster, and it goes all the way till it gets really, really close to that dotted line. And I don't know if you can quite see it, but you can still see the dotted line between it, right? Because I set it to stop at 0.99 the speed of light, so 99% the speed of light. In fact, we've never even been able to accelerate even a tiny little electron to the speed of light. Despite those huge, giant particle accelerators that we have, like that go under multiple countries and things, we still can't even get one of those to the speed of light. All right? It's just, it takes an infinite amount of energy to do this. Those other things I turned off, these are different lines of constants. So let me put this back that way. In fact, I'll turn off the CT axis. So these purple lines, this would be a line If you were to stay on that purple line, it would basically be the idea of you staying stationary from your perspective on a planet. Okay, those are lines of stationary because in order to be on the planet, it's like you're accelerating upward, right? Remember how we said that? We're standing on this planet, it's like we're being accelerated up at 9.8 meters per second squared. The shape of our path, if we drew it out on the side, would be one of those shapes. And it's a hyperbola. In fact, it asymptotes to those light lines without ever touching them. Okay? Over here, you can add this back on. These are times, if you could freeze time and stay at a point of 0 time change, you would have to move along one of those parabolas, hyperbolas, where you would get closer and closer to that light line and never cross it, and then that would be like a frozen instant time. If you could do it. I'm not saying we're doing it. If you could, that's what you would do. Now, quick question. Earlier, I'm really running out of time. Earlier, I said something about a black hole called the event horizon. What was interesting about the event horizon? What did I say? You could never do with it.
Escape it.
You couldn't escape it. What did I say on here you could never get out of?
Speed of light.
Huh? The light cone. I said you couldn't get outside this light cone. And we also said that we're not going to differentiate between gravity and motion, correct? So it turns out, and I may have to refresh this one, we can actually diagram out, oops, everything turned on again. Our constant proper time or constant time. We'll leave our light cone on. Don't want that, don't want that, don't want that, don't want that yet. But we can say, this is a black hole. If you are inside that light cone, you can never get outside of it. That's the same thing that happens inside the event horizon. You get inside it, you can never get outside of it. So if we're treating accelerations the same as gravity, which by all we can tell, they are identical, we can just look at this and put some accelerations in it and model a black hole. So what we're going to do is we're going to say that that light line right there is our event horizon. If we are in a spaceship and we don't want to fall into the black hole, we have to fire our booster rockets to hover above it and stay in orbit. Because if we stop, it's going to just pull us in, correct? So we have to constantly accelerate away from it to stay at a certain height above the black hole. Well, as we just said, that's this. So we'd be on one of those lines. In fact, I even picked one. Here's our light line for the spaceship. Just get rid of those other ones. There you go. This green line, this is us hovering above the black hole, constantly accelerating away from it to avoid falling into it. We okay with that? All right. Now, we're going to have somebody or something fall off our spaceship and go into the black hole. Okay? It gets booted off in the other direction. And we're going to put this on here. And we have a falling object. There it goes. That's our falling object. Now, from the falling object's perspective, it's really just going at a constant speed the other way. It's in free fall. Free fall, if you're in free fall, so there's the idea. You jump out of an airplane, you're not rushing down towards the ground is rushing up to you. The ground is accelerating you. You're actually just in nothing. You're just in weightlessness. There's no acceleration to you. It's the ground that's accelerating up to you. And that weird feeling you get, like on a roller coaster when you go down, is not the feeling of acceleration, it's the feeling of not accelerating. Because you get in that free fall. So you're used to always being accelerated, just that way. So this thing stops being accelerated, so it's going to go in a straight line. It's not going to change its speed or anything like that. It's not going to curve off. And it's just going to fall into the black hole. Now, from its perspective, it just falls right in and passes through that event horizon like it was nothing, correct? But what happens if we turn on some light lines from our falling object that we're looking back at? Say the falling object was like, it was going to flash every second or something like that. Well, we'd see the first flash, and it would take this amount of time. And then the next flash would take longer. And then the next flash would take longer. In fact, and it's not just taking like the first flash took 1 second, the next one took 2 seconds, the next one took 3. It's ever increasing because we're curving away. So if we're watching this thing flash, it starts off and it's flashing. And then as it gets closer and closer to that event horizon, it starts to slow down. And as we stay along this line, we get closer and closer to this event horizon ourselves. And in fact, that last little bit of light before it crosses that event horizon, we're going to be speeding away from it along the event horizon, that light line, and waiting for it to catch up to us. And so we would watch this thing flash, and it would look like it was following the black hole. We'd never see it cross the black hole line. It would appear to slow down and slow down and slow down and basically take forever to cross it, and eventually come to a stop, because we'd be speeding off forever, and that last bit of light would be speeding off forever trying to get to us. And so it would appear to slow down. All right? Now, from the person falling into the black hole's perspective, we can kind of turn those ones off. We can do a bunch of light coming from us to them. Now, once they cross the event horizon, there's no reason they can't still see us. Light can go into it, it just can't come out, right? So we can send light to them, we can send signals to them. And what would they see? They'd see us be right here, a little bit away from them, a little bit away from them, and then look, as they follow this black hole, how far they get away from us real fast. What they would see is they would see us shrinking away, collapsing, shrinking away, and just speeding off away from them, basically infinitely fast. For them, they wouldn't feel any time dilation. It would feel like nothing at all. They'd just fall in. This is assuming they're not running into other objects that are falling in, like dust and rocks and stuff like that, which I think if you remember the movie, a lot of that happens, right? It ends up tearing his ship apart. But assuming that doesn't happen, you just look out and you just see it shrink away into nothing. Okay? And that's what we see there. So I want to show this to you. And I hope it's still in this right spot. Doesn't look like it is. Okay. Let's try this. Okay, so there's Gargantua from the movie. Which, by the way, you see how that light goes up over the top of it? That's actually just a disk of light all the way around it. It's just that it's so strong it bends the light over and it looks like it's coming from the top of it.
Okay, so on one hand, I was
Which is also a reason why you can never hide behind a black hole. Because if you hide on the opposite side of it, the light just goes up, bends over, and the person can still see you. So don't hide behind it. Alright, so here they are. Where is this when he calls it? Oh, she's upset. He's gonna go. And there's one part here I want you to watch for it. So here he goes into it. And it's gonna be in the upper, kind of the top of the screen, upper right, if I remember correctly. But watch what happens as he's looking out into space. Watch what happens with what they did. I always thought this was so cool when I saw this the first time. I was like, oh, watch it. See space shrinking away? You want to see that one more time? Right? That was cool. I think it's cool. I always thought that was such a neat effect. Wait, there it is. See? And it's starting to shrink and accelerate away, and all the galaxies, it's all just getting smaller and squishing away. Including that circle around it that would have been the accretion disk that we just went through, that big lit up disk around it. Alright? Kind of cool, huh? So now, you understand at least that part, that I'm fairly certain a lot of people didn't even notice that little tiny little bit in there. And you're welcome for spending like 20 minutes explaining that one tiny little bit of why that shrinks away like that. I hope that was worth it for you. So, where do I want to go here? Current slide. Okay? So, big question. In the movie, what happens when he finally gets out of that black hole? What's the one thing he tells his daughter about it? When I'm out there, going near the speed of light or near a black hole, what does he tell her is going to happen? He says that their watches are going to get out of sync. Because he gave her that watch, right? And he says that when he's going really fast, his time is going to slow down. And when he got back, they can compare those watches and see how much time he was behind. Of course, ultimately, when he gets back at the end, it's been way long. I don't think her watch is probably even still working. But time went very different. In fact, he gets back and his daughter is way older than him, right? She's very, very old and living there. So what this basically is this is a forward travel through time. So when we say, can we travel through time? The answer is yes. In fact, I would even say, we're all doing it right now. You are further ahead of time right now than you were when I started saying that you're traveling through time right now. You're traveling forward through it. All right? And you can actually travel forward faster through time by going really fast or getting near a black hole. Okay? You want to be like, you know what? I want to see what the future's really like. Get up there, fly off in space really fast, and then come back and be like, oh, it's the future. Look at that. I traveled 100 years into the future in 5 minutes or something. Okay? You'd have to be going pretty fast. But you can basically do that by going really fast or getting near a black hole, which would also make you go really fast. So yes, we can travel to the future and we can do it at different rates. Can we travel backwards through time? So far, no. Not with what we know about this, we cannot. There are some pretty crazy ideas where you can use this relativity stuff, but then you have to have like special kinds of matter that don't seem to exist to be able to do it. And there's weird things you can do with that, and no one even really knows what that means, because like if you could travel back in time and you could like, go back in time 5 minutes and stop yourself from going back in time, then you get those paradox things, right? Or the old grandfather thing where like if you went back in time and shot your grandfather while he was a teenager, then you'd never be born, which means you never went back and shot your grandfather, which means that your grandfather did go along when you were born, which means you could go back and shoot him, but then, you see what I'm saying? So there are those kind of issues with the backwards time travel. So I'm not so sure that God put us in a universe where we can, because it would cause us some serious problems. All right? Another interesting thing about this. Who remembers that scene? Where is this?
Inside.
Inside the black hole, right? He gets inside the black hole, and what can he do in there? What has he discovered he can do? He can move around through time, right? All of this is one location. It's one location in space, but it's spread out like time is spread out like space, and space is acting like a single moment, or space is acting like a single. It's one location, right? So that's kind of weird. Now, this is a little bit. This is kind of speculation because, like I said, we've never been inside a black hole, and the math does get kind of funky. But the idea is, if you go inside a black hole, once you cross that event horizon, time and space switch roles. And so that's what they were going for here. I have no idea what it would actually look like. And he even said the advanced whatever species built this so that he could understand how it was working in there, right? So this was supposed to be a representation of time acting like space and space acting like time, okay? And the reason for that is there is something called a metric. Outside the event horizon, you have what's called a 4 vector. You have 3 spatial dimensions and 1 time dimension. And it turns out to make a hyperbolic space, anybody remember? So if I want to make circles or ellipses, it's x squared plus y squared equals r squared, correct? Does anybody know the equation for a hyperbola?
1 over x.
Anybody?
Is it?
It's actually x squared minus y squared equals r squared. That makes a hyperbola. And much like you can have the unit circle, we can actually do a unit hyperbola. We can do a lot of the same things. That's where, like, you ever heard of hyperbolic cosines and hyperbolic sines? Those come from the unit hyperbola. Okay? Yes, you know that. Well then. So, and it looks like this. So you would basically say space is hyperbolic, like we saw in the Minkowski diagram. We saw all those hyperbolas. And you would pick it and you'd say something like, all the spatial dimensions are positive, and the time one is negative. That gives us that hyperbolic shape. Okay? But one interesting thing happens, and I won't show you the math on this. Not that I even could probably even remember the math of it. It has been so long since I've seen it. But when you cross that event horizon, something very interesting happens. All the signs flip-flop. All the spatial dimension signs become opposite. They become negative. And the time sign becomes positive. It switches. And so what they say with this is, because we don't really know how to interpret this, it is interpretation, is that time becomes space-like and space becomes time-like. Okay, and so it is that switching of the metric, that switching of signs on time and space in the map of a black hole, that is that idea they were going for there. So, little something interesting there, that tesseract thing. Yeah. Like I said, it's like, we don't really know what happens inside a black hole. And in fact, that was the big problem in the movie, wasn't it? We don't know what's happening inside the black hole. And it was only by going into it that the advanced people or whatever allowed him to communicate information, outside of it, because nothing goes fast in that. But what we do seem to know is there is something big and crazy in there. All right, and I guess the only way to find out at this moment would be to find a black hole, which you couldn't get to in 80,000 years. You couldn't make it. Fastest we've ever gone, humans, or the fastest man-made object. We just can't get there. And then you'd have to go inside it. But up until then, it's speculation. But it seems to be pretty accurate and pretty consistent. So it's very, very interesting to me. Okay? Yeah. I thought they did an amazing job in this movie. In fact, one of the things I remember Kip Thorne saying was that planet, Miller's planet, I forgot to say this earlier, is so close to that black hole that it would be like football shaped. It would be so stretched out from the gravitational forces on it. All right, and that's why you have those big giant waves as the planet orbited underneath those big waves. Those were the big football shaped parts of it. The waves that were coming around as it orbited. Or not orbited. Oh, hey, no, skip, don't restart now. Sorry, it's trying to do a patch in upstate or something. So, yeah, very interesting stuff, I would say. And it is speculative, but it is grounded in being very consistent with the stuff we can measure. So, anyway, oh, it's because I clicked off to get rid of that thing. Now it doesn't want to let me do that, so let's try this. Questions? Any parts of it, anything, Thank you, no applause. Yes.
Can you address spaghettification?
Sure. Where'd you hear that? Because I don't remember saying that.
You didn't.
I know I did. So that is actually something from what I was talking about, like it being a football shape.
Mm-hmm.
So you can imagine you're standing right here on the planet right now, and right now my feet are closer to the planet than my head, which means the force of gravity on my feet is greater than that on my head, right? So if we had someone who was really super tall, like Million Mile Man, standing on the planet, the force of gravity on his feet would be way stronger than the force on his head. And in fact, it would be so much of a difference that it would pull his feet down and accelerate them faster. Like if he was falling, his feet would accelerate faster than his head, and what would that do? Stretch him out. In fact, it would break him apart. There was it the Shoemaker-Levy comet that hit Jupiter? It was this comet. Go look it up. It's pretty cool. It hit Jupiter, and we were going to watch it. And as it got close to Jupiter, it actually broke apart because of that gravitational, they're called tidal forces that act on it. You'd also can imagine that the sides of the planet pulling you in, because you'd be so wide, would pull you in this way. They pull at angles towards the center of the planet, right? And that would squish you. So you get stretched and squished. And so the idea is, if you're falling into a black hole feet first, your feet would get stretched out, you'd get squished, you'd get stretched out, and you become this long, thin, spaghetti noodle thing falling into it.
Should they have included anything like that?
They could have. They talked about not surviving going across the event horizon unless you were going really, really fast as to get through those tidal forces before they could destroy you. So yes, they did kind of talk about it without using the word spaghettification.
Okay.
But that is what people call it, so it's right there. Anything else? Yeah.
So I have two questions. One, how does is the force of gravity
Whoa. Stop you right there. And maybe I wasn't clear on this. Gravity is not a force.
Is the acceleration of gravity
There you go.
a responsibility? Is it caused by mass, or is it caused by particulate forces?
So, according to relativity, which constantly keeps getting verified, which is weird because so does quantum mechanics, and they disagree on what the cause of gravity is. It is kind of funny. You watch it and you're like, oh look, we have a new experiment that shows quantum mechanics is so accurate, quantum field theory, woo! And then like, it's almost always followed on the heels of, oh look, we have a new experiment that shows exactly how accurate relativity is and how great it is, and they disagree on this part. But sticking to relativity, what we're talking about here is matter warps space-time, and space-time tells matter how to move. So you put a bunch of mass in one spot, it'll warp space-time. Probably seen those pictures where they stretch out the sheet and they put the balls on it and it makes the indentations. That's what they're trying to show, is a warping of that space-time, and then everything else that's around it, all that matter, has to move according to how that's warped. So we would call it a warping of space-time by matter, which then controls how the matter moves, which is what collects it.
And then my second question was, there are theorems that are super colliders. If something were to go catastrophically wrong, could create a black hole. Given the rough energy that would be produced by that, what would be the effects on the planet?
We wouldn't
if
notice.
such a thing. We wouldn't notice.
That black hole would be so teeny tiny, it probably wouldn't live very long at all. The smaller a black hole is, the faster it evaporates and destroys. So if you made a black hole in one of those colliders, it would probably last, fractions of seconds. And if it didn't and it stayed stable, it would fall down right to the center of our planet. And if anybody's had physics with me, you would know that, for example, if the entire planet turned into a black hole right now, the moon wouldn't notice. So if we took a tiny little bit of the mass on our planet, turned it into a black hole, let it fall, no, it wouldn't change the gravitational field here or anything. It wouldn't notice. So not worried about that at all. Yeah.
So you were talking about how the speed of light is always ahead of us.
Mm-hmm.
So to assume the speed of light, it moves, so it has a direction. Technically, I don't know how you would do this, but if you wanted to catch up to it, could you go around the other way, get in front of it, and then be faster than it?
Well, what's the shortest distance between 2 points?
Straight line.
The straight line.
Straight line. So going around on a longer path at a slower speed, it seems like that's what you're asking me. If we go a longer path at a shorter speed, would we catch up to it? I mean, if we could get it to go in a circle, definitely we could send light that way and go the other way. It's fiber optics bend light around like that. Of course, they don't really bend it; they refract it around. But yeah, if we could go faster than the speed of light, it'd be kind of cool. You could go faster than the speed of light, stop, turn around with a giant telescope, and look back and see yourself as a kid. Right? Look back down here and be like, oh, look, that was the day that my mind was blown by Dr. Almand's talk on Interstellar. You could somehow look through the ceilings and all that stuff, but you'd be like, there I was, look at that, so cool. Any other questions? Was there anything about Interstellar that I missed that you were interested in knowing about that I didn't get to? I stayed mostly on the black hole stuff.
Oh, I have a question.
Yeah.
Okay, so Miller's planet, right?
Yeah.
Supposedly it was next to this other massive gravitational thing. So wouldn't the gravity on that, considering how massive the waves were, wouldn't that have crushed the people who were on the planet?
So, no. Miller's planet wasn't the one making the giant gravity and slowing it down. It was the black hole they were near.
True. Okay.
If you tried to get on the surface of the object making that much gravity, yes, that'd be like getting on the black hole.
Okay.
Right, but they were on something, I think they described it as being a ball that's going around the rim. It's right on the edge of the black hole there. And so when you got there, you'd be in a pretty uniform part of that gravitational field. So I'd be okay. You'd have to be on the giant planet. Yeah.
So does it orbit the black hole?
Yeah.
Oh, okay.
Otherwise it'd fall in. And to stay in orbit, what do you have to do? You have to accelerate away from it. So it's basically accelerating away from the black hole, which again, we talked about acceleration in physics, right? Either changing speed or turning. Yeah.
What about the hand while they're going through space?
Oh yeah, that one's very, so, of course you have to bring that one up. I have no idea, or anybody else, what would happen inside a wormhole. A wormhole, the way general relativity works is if you can find what is called a metric for it, and the metric actually fits Einstein's equations and solves them. Kind of like finding, oh, I found that 2 solves this equation, but I also found that -8 does too. So anything you can find that's a solution to it should be possible if you have the right kind of matter. But again, that wormhole thing is supposed to be one that you do need some special kind of matter that we don't know that exists to keep that open. And so somehow they were able to do it. I have no idea what happened inside there. That was kind of the only part where I thought, wait a second, how did he left, but then he went through the wormhole at the same time they did from the beginning of the movie, and then he came out, but it was still way later. Like, yeah, that part, I'm not really sure on that part. That part I think they might not have asked too much permission on, or maybe they did, and Kip Thorne he definitely knows more than I do, so maybe there is something there. But that one I've never been able to figure out how that was supposed to be possible. Sorry.
It's all
Thanks
right.
for picking the one thing I think I can't explain.
That's my job.
Anybody else? No? Okay, one more. Yeah.
Okay, I'm gonna be honest, I was having a little bit of a hard time following.
That's okay.
Because this is like kind of confusing to me, but
Me too.
it's very interesting though. So you're saying that when an object goes past the horizon of a black hole, we see it go super slowly.
We see it slowing down. Yes.
We see it slowing down. What's it really doing?
From its perspective or whose perspective?
I guess
It's all relativity. You have to have a perspective you're looking at it from.
okay.
From our perspective, it's slowing down and then coming to a halt and it's freezing.
And that's because it's traveling. That's because we're traveling away.
Well, from our perspective, we're not traveling away from the black hole. We're just orbiting above it. So it's time dilation, slowing it down. From its perspective, we're accelerating away, and it just sees us shrink and accelerate away. And the point is that we can't tell which one is true. Like the thing with the twins. The one twin goes off and says, I'm the older twin. The other twin says, no, I'm the older twin. They're seeing the same thing. It's the same event. One twin leaving, but they disagree on the outcome. The trick to this is, all right, let's put it this way. You want to know which twin is older? If the twin that shot off in the spaceship were to stop, turn around and come back, he'd be the younger twin. He went through the acceleration. Gravity is what really does the time dilation. He went through the acceleration, he'd come back and be the slow one. If the twin that went off in space just kept going, and the one on Earth got in a faster spaceship and took off after him and caught up to him, the one that caught up to him and went over to him, he'd be the younger twin. So, we're watching this guy fall into the black hole. If he somehow, before he crosses that event horizon, turns on his booster jet and flies back to us, we on the ships would have been the one that was right. He would have slowed down. If we turn around and then suddenly launch ourselves at him into the black hole, he's going to be the right one. It depends who does these things. Once you bring everybody back together, they agree. It just depends on how you bring them back together as to what they agreed upon ultimately. Okay? Because you can imagine if you started going back towards the guy in the black hole, you'd start running through those flashing lights really, really fast, and you'd start seeing him going really fast, and you'd catch up to him like that. So I first heard about this. I'm going to give a little shout out to Mr. Sam Allen. He told me this at the bottom of the staircase at Bloomingdale High School one day, and he told me about this thing here. Oh, it's trying to make that do that thing. This. He told me about, where was it? This. He told me this one day, right? It was senior year in high school. I just started taking physics. I thought it was so interesting. He told me about this. And I remember him sitting there saying, oh, and then you do this and this and this. And he did it right on the staircase. And I've been hooked on physics since then. That was like, I was amazed. I went home, this was before we had the internet. And I was like before everybody had it in their houses, you know. I went home, I was in the encyclopedias looking everything I could up about relativity. I've thought about it every day pretty much ever since then. Every time I have like free time, I'm mowing the yard, I'm doing this. This is so often something I'm thinking of. So when you say you had a hard time, I'm asking you to catch up to what I think, which is still very incomplete, and there are still things that confuse me about this. But, you know, for 3 decades ago, almost. So I've been thinking about this for 30 years, you've been thinking about it for an hour. And it still confuses me. So it took Einstein 10 years to finally decide what he had and publish this. And he only published it without fully understanding it because somebody else was going to do it. That had realized what he was doing and was like, no, I'm going to go ahead and publish it. But he went ahead and did it because he was getting forced to. And he didn't still fully understand everything about it. I don't know if anybody does. I don't know if anybody understands anything about everything, so, or everything about anything. Yeah. Okay? So go check out my other videos if you want. Ask me other questions. Oh my gosh. Okay, one more.
In the class, if you move sideway, same speed of light, then different story happens.
If what?
If we move sideway,
This is moving sideways.
side speed is the same as the speed of light,
No. If it was,
then
well, we can't go the speed of light. We've found that doesn't work. Even mathematically, it doesn't work, and also through what are called Lorentz transformations.
for shooting, so same speed, then
So this is going at a constant speed to the side.
so moving side is so fast, then different story, isn't it?
No, it would just be a bigger time dilation. It would just be a bigger effect. Like if we made the thing moving sideways faster and faster and faster, it would just become a greater and greater effect. Is that what you're asking me?
You said that even though it's move slowly, then time is the same, right?
Well, if it's moving slowly, it has hardly any effect and we don't notice it.
Yeah, but
Like
if
riding
you-
around in your
if
car.
you're moving this side, it is the same as the light of speed, then
It's the same as what?
speed of light.
Yeah, well, we can't do that though.
I know, but if you
So Einstein thought very long and hard about that. What would it mean to move at the speed of light? And he thought about something like, say, if you were holding a mirror out in front of you and you were going at the speed of light, and light came off of you going through the mirror, would you just never be able to see yourself because the light coming from you would never reach it? Right? And then it was this whole Michelson-Morley thing where no matter how fast you go, the speed of light is always that much faster than you. So no matter how fast you're going to the side, you still think the speed of light is that much faster than you in that direction. So if you were going this way, and the guy standing still says, he is going so crazy fast, it's near the speed of light, you're on there, and you have your laser pointer, and you point it out in the direction that you're going, the speed of light is still that much faster than you, from your perspective. And my perspective. All the perspectives. So look up the Lorentz transformations. And that's what's not, so we had the original Galilean transformations from Galileo way back in the day. And then Lorentz transformations are actually what all this Minkowski space is based upon. Everything. And in them you can see that no matter what you do, no matter how you're moving, the speed of light is always that much faster than you. It's baked in it mathematically and as for any experiment we've ever been able to do. It always seems to, if you point it in the direction you're going and behind you, and you measure the speed both ways, it seems the same.
light can go through black hole?
It can go into it, can't come back out once it crosses the event horizon. That's what makes it black, right? Nothing can come back out of it, you can't see it. There's also a point around the black hole called the photon sphere, where you can actually get light to orbit it. The light would orbit a black hole. There's a photon sphere.
And during the going to the center, then speed is going to be decreasing?
As it goes in?
Yeah.
Well, there's a couple ways you can think of it. You can think of it as it goes in. So as far as the light never escaping, you could think of it as like if we try to throw something up, it'll eventually come back down. You can also work out that as like in that one picture I showed us, light was going up to the satellite, it was stretching out. Then it causes it to stretch out so infinitely far that it's not a wave anymore, and so the light never gets out according to that. There's like multiple ways you can kind of work it out from different perspectives, and it all says the same thing: it can't get out. It can go in, can't get out. And again, it depends on that perspective. It's that relativity thing. I can show you more of it if you want me to later. Yeah? We'll sit down and talk about it. I love this stuff. So next math meeting. Let's Or lunch tomorrow. Okay. All right, guys?
Mhm.
Oh, Madeline, yes.
Do you need a piece of paper?
Oh, I do. If you're one of my students who wants to put your attendance in here, I need you to sign your name on a piece of paper or write it legibly. Please don't sign for people that weren't here. And just write your name on it, and I'll make sure that you get put in there. Okay? Write what class you're into, day and time. Like it's a Monday, Wednesday, Friday.
Yeah, I'm in class.
Physics, you just have to tell me physics. Is that
Can I
fine?
borrow a pencil?
Yeah, of course.
Thanks for coming.